Okay, our next speaker is Jonathan Howe. He's a professor at MIT, professor of aerospace engineering. He is an expert in autonomous navigation under uncertainty, and his work sets in motion a variety of ground and aerial vehicles. The of his talk promises a fascinating mix of insights for modeling interactions between pedestrians and vehicles, for online update of these learned models, for communication between vehicles and stationary infrastructure to improve the understanding of pedestrian motion, and finally for safety and robustness guarantees of the learned models. So without taking any more of your time, I would like to welcome Professor Howe to our stage.
Great, thank you very much. And hopefully you can see my slides. So what I'd like to talk to you today is about context-aware learning of human motion prediction for safe autonomous driving. And so just in terms of a quick background, I mean, I came to this work predominantly when we were thinking about path planning for vehicles. And so often when you think about planning, say in static environments, there's a lot of work thinking about the vehicle itself and the dynamics of it and the localization of that vehicle. As you start then moving into thinking about dynamic environments, you then obviously have to start thinking much more about what how the world is evolving outside. And then of course the question being how long or how accurately one can make those predictions and then use that information in the actual planning of the vehicle itself. So when I started work on the urban challenge back in 2006, 2007, it was a long time ago now. So the beginnings of a lot of the work now on autonomous vehicles, but at that time we had to start thinking about how other vehicles might be moving. Some of them robots, some of them human driven. No pedestrians at that time, but then we quickly moved on to thinking about how other agents might come into play in some of that prediction work as well. So I'll be talking today about work from Gonaz and Michael, two of the postdocs in my group. And just a quick shout out, happy Memorial Day to the other people in the US out there. And thank you for the invitation to talk at this workshop. So as just mentioned in the previous talk, and I'm sure some of the others earlier today, it was a bit early for me to get up, but there are numerous applications for sort of the use of autonomy alongside of the humans themselves. I highlight a couple of them here. Obviously, there's the big push in the autonomy industry. Everybody now having the selfie drones. And so that's one area, as was just mentioned, that I've spent quite a bit of time doing work, again, path planning, but also thinking about where the agent is, in this case, the person trying to film where they are and where they might be going. You might have also seen some of the work we've done on robot driving as well, and thinking in that particular case about the social aspects of determining how to navigate around humans themselves. But there's many other applications, and I'm one of the sort of, I haven't seen it recently, but this one here, where when you're in the airport and there's the vehicle going beep, 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 as they try to get people out of the way, but driving in a very complex environment, the human-driven vehicles actually tend to do quite well. I often see this as one of sort of those prize challenge problems. Could you do this autonomously? And as I'll get to in a second, of course, you know, one of the aspects about the differences about driving in that type of environment is just how random people tend to be compared to driving in a road network. So there is a lot of work, as we've all seen, in terms of the autonomous vehicles and handling sort of all those sort of other types of events that might happen, shown here with sort of just kids jumping on their bikes and driving out. And of course, just handling those cases that are not really part of the rules of the road, and understanding or anticipating that this might happen at, say, a crosswalk like this. And so handling those types of things. So again, with a lot of this work is sort of understanding that pedestrian behavior to try to inform the path planning algorithms. And that's predominantly the way that we've been thinking and focusing on this work. So we have done path planning, but again, as I've said, say in this case here with the robot, you're sort of trying to populate in that world some future prediction capability for both your vehicle, but also the other agents around you. And that's the reason we've been looking at the path planning algorithms as for many others. So some of the challenges that we, as a result of that type of work and that objective, have been trying to focus on is thinking about sort of some of the data collection techniques. And so I'll show you some work here. This is Justin, who now actually works at Ford. He was actually doing some mobility work and thinking there in a particular case of trying to get to the level of understanding what the demand traffic was in a network, which in that case was just MIT, where we were looking about robo-taxi, but thinking about pre-positioning assets, trying to understand where the demand might be, thinking about things like class time and the class cycle, and understanding how that type of cycle might interact with the demand. This is one of the intersections nearby us where Gonaz sort of set up her camera system. And so we were actually using a combination of LiDAR and camera, similar to what was just discussed. I mean, you need LiDAR in this case for range, and then you need camera for identification. So a lot of this ends up being a semantic classification problem. And so you need to be able to identify both the object and track it, which you can do with Velodyne, but do they also need to be able to classify it as a pedestrian as opposed to something else? And so you can start doing the ID and re-ID. And so when it's close by, you can use an RGBD camera, but when it's far away, as it is on the scale of this intersection, you need now to start thinking about Velodyne and camera. And so that's what some of the data sets we'll talk about, but getting more data sets like that, which then can be written in a similar form and then used to learn upon, is one of the key challenges here, I think. Certifiability, we'll talk about that as we get to it, but we're all familiar with the deadly crash situation that occurred at Tempe. And of course, situations like that are cases where you need to be able to anticipate better in that case, what a human might be doing in an environment that was unexpected, and then anticipate it better. Of course, situations that we often have to deal with when we're working in a city is the context. And so, what's up here, a little bit less bright than you might find traffic lights, a little bit hard to identify, and unfortunately not consistent at all. We've done a study of the number of devices like this that are in the neighborhood of MIT, and it was on the order of 5 or 6. There's just no consistency in what's actually being shown. The combination of the red hand being stopped and the flashing red hands, countdown clocks, walking men, in this case, it could be white, could be green, all kinds of different things. And so it's A, faint, and B, a little less clear what you're even looking for. So trying to account for that in the context, but also sort of understanding even what the context would be. Continual learning sort of tied into the data collection is just sort of over time an ability to continue to improve the prediction error and find methodologies and techniques that actually, or algorithms that actually allow you to combine extra data in over time. And then, although an empty corridor, I mean, what's sort of highlighted here with the arrows is sort of the, the social context. And so there's an indication here, sort of, and again, if it was an arrow on the ground, it would be easy. You just sort of have to look for the arrow. The point being you're supposed to pass on, walk down this side as opposed to walking on that side. But one of the things we were looking for, as was just discussed with the robot, you don't want a robot necessarily falling too close. You don't want to sort of drive up behind somebody, you start freaking them out. They're not necessarily that comfortable having a robot sort of nipping at the heels. But there's also a question of, do you pass somebody? If you're going to pass them, on what direction do you pass them? If you're familiar with MIT, we have this notion of an infinite corridor, which is just a long corridor that sort of connects a lot of the buildings together. But if typically on a busy day or pretty much in between classes, it'll be 2 or 3 people on each side walking down in opposite direction. And I often sort of pose that as another one of those challenge problems of, could you drive a vehicle down that corridor at faster than the average walking speed? I mean, it might be easy to generate a vehicle that just sort of, sits behind the slow person. And again, maybe try to be, not super annoying by just sitting behind them. But that isn't the question. The question is, can you pass them? But to pass them requires you go into the opposing traffic. So you got to find that gap, identify that it's sort of worth doing, and then effectively speed up and jump around and get in front. People can do it all the time. Can a robot do it? And those types of sort of, understanding that social context in the sense of what's acceptable, what's not, to what extent can you sort of cut somebody off and not, the types of things that obviously depend a lot on where you are, what you're doing, that sort of part of MIT culture. If you did that here, maybe okay. If you behave that way at, say, another school, that might be completely unacceptable. So understanding the culture of the environment you're in and being able to adapt to that social environment, I think is very important. And also that tends to be a function of time of day as well, how you might behave. So as I say, one of the types of challenges then we're looking at here, and one of the differences, say for us working with autonomous vehicles, and so autonomous vehicles for us is sort of cars/robots, moves into UAVs, but I'm less thinking about that here. but just dealing with the high uncertainty in that pedestrian motion. So, again, the key challenge here being that, with cars, you might expect there to be rules of the road. I mean, there are rules of the road. People are supposed to follow them. They probably won't, or they may not. And again, if you're familiar with Boston, you know how unlikely they are to obey the rules of the road. The point is that when you're thinking about people, say pedestrians and cyclists, I mean, there's almost no rules of the road. Certainly for pedestrians, and the notion being that they will jaywalk or just run across as they see fit. Cyclists, again, supposed to be following the rules a little bit more. On the other hand, again, that's a little bit questionable as to whether or not they do. So we've got that high degree of uncertainty. And even if you were dealing with people on a sidewalk and you were sort of on the sidewalk yourself as a robot doing a delivery task, you're dealing with the abrupt direction changes that might occur simply because people change their mind. I mean, it's just, oh, I forgot something and turn around. But if you're a car trying to deal with it, you've got to deal with people darting in and out, and sort of situations and crosswalks not being the way you might anticipate. So built into all this is sort of a hidden intent of the pedestrian. And so we use intent as a way of describing, as it was just discussed in the previous talk, this notion of sort of what are they going to be doing next? There's an element of prediction which has to do with sort of the path they're taking, but intent is more about the goal, or we think sometimes of sub goals. And so when I use the word intent, I'm often thinking about sort of, what's the longer term goal, or sub goal that they might have in mind, which is sort of somewhat driving the behavior that I'm seeing in a local extent. And as I mentioned before, there's the environmental context, understanding traffic lights, crosswalks, and just because the hand starts flashing doesn't mean people are going to stop. In fact, it might mean that they run out more. And sort of, with the understanding that they have that time is now getting short and they want to jump out there and get going. And of course, there's the intersection geometry itself is going to end up in influencing how pedestrians might actually sort of cross over things. And they're anticipating that there'll be less traffic on one part of the road. And so they might sort of just dart across that and they're trying to get to another part of the intersection themselves. So those are in my mind, a lot of the challenges. I'll highlight some of those as we go along. This is actually, I think, a video from Cornell. One of the things they're looking at here was just the interaction aspect of things. And so there's a bunch of people clumping together. So in this particular case, one of the challenges is not only ID, but the re-ID problem. Can you actually track in a longer term sense how those objects are moving? And as I said before, it's a semantic labeling problem. So part of the re-ID is actually looking for things other than just blobs, right? You have to understand this object in a context sense, which will help you understand how to track it on the other side. And so you're looking at things like color, shape, size, and just so that then you have an ability as they group together to then sort of grab that agent and connect that onto it as a similar sort of identification number on the other side. And again, if you're familiar with these notions of tracking, the ID number is important because then you have that longer term sense of where they went. Otherwise, you just end up with a whole bunch of paths and they haven't really been labeled as being a specific agent. So one of the things we've been looking at then is that, as it says here, most of the data-driven approaches are trained on specific data sets and don't generalize as a result to the new data sets or environments. And that's one of the challenges we're looking to address. And so we looked at transferable techniques that I'll get to in a second. And that many of the others actually sort of end up being trained offline based on data sets, using the entire data set, but then can't be updated incrementally when new data comes in. And so that's part of what we're looking at as we work with some of the companies on dealing with these these autonomous vehicles and autonomous intersection situations. We're looking at the sort of continual development of data and trying to find techniques which are then able to handle both incrementally that data set as it comes in, but also can transfer to new environments as the car itself perhaps goes to new environments as well. So the transferable and context-aware motion prediction, again, if you're familiar with the geometry, Boston's an old town. A lot of other cities have sort of environments like this, but not many intersections in the Boston area are actually 90 degrees. And as a result of that, we end up in a situation where a lot of the behavior learning you might do in an environment that, say, a 90-degree intersection like this is interesting, but doesn't transfer well to other intersections. And so again, if you're thinking about an incremental learning, you want to make sure you have a way of essentially accumulating models, but writing them in a representational form, which can then be sort of compared to other new models as they come in. And so you might learn or collect new data at each new intersection, but each new intersection then is a slightly different geometry. You want to be able to combine them into a coherent set. So the idea then is try to incorporate the context that contains the specific spatial geometric characteristics and then be transferable to these different intersections. So what we've been looking at then is this technique. It has the acronym that doesn't roll off your tongue. It's TASNFC, but it's transferable, augmented, semi-negative sparse coding. So the first work was in the augmented sparse negative coding, was semi-negative sparse coding. And then we added the piece in this more recent work in 2018 that looked at highlighting the transferability. And the key thing was to come up with a representation that was based on this contravariant distance to the curb side. And so effectively, it's a coordinate change from the curb side itself. So there's sort of something defined to be the intersection corner with the curb side itself sort of highlighted in black here, but then we sort of convert it into a new coordinate frame. And so once we have a standard way of sort of doing that transfer for each of the intersections we're working in, then we have a standard coordinate system that can work in and do comparisons between the two. And so again, just to highlight, not many of the intersections around MIT are orthogonal. And so this is perhaps one of the closest that's near us, but a lot of them end up looking like this. And so your roads come in and then go off like that. And so this is a busy neighborhood in part because there's a subway station off to the right here. And so there's a lot, and a lot of businesses like Google and Amazon are up here. And so there's a lot of traffic moving back and forth. And so part of what we're looking at is that sort of relationship, so we can learn from one side of the environment to the other and how to combine the two together. So what we ended up building on was something called SILA, which I'll highlight in a second as to exactly what that is. But what it is looking at is a way of incremental learning. And so what we're able to do then is, as we get different data sets, we can actually combine them together and pull in the different data sets. And a giant table here at the bottom, but as is often the case with this work, you need to be looking at many different data sets, as shown by the columns here, as well as many different algorithms. So we have a whole bunch of different comparative algorithms here, as well as a bunch of ours sitting at the bottom. And we're looking at the standard sort of average and final displacement errors shown here in the tables by the two numbers. And the point is just to highlight that, down here, if you look over average over all the different data sets, we end up with about 11% improvement in the average prediction error compared to the state of the art. But furthermore, we end up with a model size that's about 1/3 the size of sort of what I'll describe as a naive incremental learning technique. And so, again, the classic problem when incremental learning is you can't just be in a situation where the model is continuous to get bigger and bigger. And that's what I'll describe as the naive approach, where you're simply combining things. You get model 1, get model 2, smush them together, and you end up with a model that's twice the size as the one you had before. That's not sustainable. What you need is a technique which can then compress as you go along. And so the fact that we can end up with a model that's doing better in terms of performance and also is able to, it does grow, but it ends up growing at a much slower rate because of the compression that we're able to do. So how does it work? Well, one of the things we were looking at then, again, we had the sort of adaptive, so there's the semi-negative sparse coding, which is effectively a way of, in this grid environment, of developing a sort of a set of motion primitives with transition probabilities. And so there's mechanisms here that end up looking as Gaussian processes trying to capture the transition probabilities. And then we have sort of what effectively is sort of macro actions for the agents. But all this has been learned based on the data. So this is sort of a data set we collected at one intersection, again, working in the contravariant sort of coordinate frame. So we can then end up with something which can be transferred. We're able then to sort of come up with the motion primitives with an understanding of where agents, the humans tend to go, and also what is the transition probabilities they tend to have between these different macro actions that they're showing. And the point is that that ends up getting written in essentially a graphical model where you have sort of one macro action with some transition probability of the other macro actions. So it's written essentially as a graph format. And the point is, if you get new data that comes in, you get a new set of data on a different intersection, because of the way we now have been able to collapse it into a consistent coordinate frame, we can then come up with a model of its own set of macro actions and transition probabilities and its own graph. And the point is we can combine these two graphs together and then fuse them. But of course, the complexity here is trying to figure out, is the red thing up here the same as the red thing down here, and the green thing's comparable? And of course, there's no labeling going on explicitly by humans, so we don't, what we need is the technique to figure out. And some of these end up overlapping and looking very similar enough that they can be combined, and then you end up with a new model that's up here, which again may end up with sort of compressions of things that look similar, or combinations of things that look similar, as well as additional new things that get added in because they sort of showed up as unique objects in the independent models. So that's where you get some of the growth. But not only are we learning and compressing and developing sort of more confidence in the macro actions, of course, we're developing and keeping and updating these transition probabilities as well. And the point being that if we can then repeat that, and again, things will continue to grow, but the idea is to try to keep the growth size as small as possible. So that's the incremental learning. As we begin to expand that into thinking about things that go beyond the size 2, we ended up with a more recent paper that came out this year. It's called SimFuse, where now what we're thinking about in this particular case, it could be sort of, autonomous vehicles, or it could be sort of different nodes at an intersection. Again, similar thing is happening where they're each developing their independent models, but if they have an opportunity to combine and fuse information together, so the green vehicle here collects a bunch of information from other objects or other agents, or it could be other sort of infrastructure nodes, then we have a situation where we can now, using a similar technique, but scaled up to a much larger size, we're able to combine all those different models together into a more coherent and consistent model for this independent agent, which then can be shared with the others as need be. Again, similar technique, everything just sort of scales up, and the point being that each agent now is communicating with its neighbors. They share their sort of their models and the transition probabilities, which then get combined. So you end up with the same graphical model I just described, but it's on a much larger scale because there's more agents involved and more models involved. And again, the key element of the complexity here is the fact that you're trying to combine and fuse things together, which just don't look exactly the same. And so you have to basically figure out, are these close enough? And if they are, then you can actually combine them. If not, they end up looking sort of separate. So it's a sort of clustering problem on the macro actions is essentially what it boils down to, but with the possibility that these clusters can be reconfigured. So we end up with a technique that handles that. And like I said, that's in the SimFuse paper we just written recently. So as I said, Godaz was out collecting data in the neighborhood around MIT and Boston, collecting sort of different geometries and things like that for the different environments and setups. So this is all experimental data that I'm showing the results for. And again, we're comparing the ADE and FDE. There aren't that many things we can compare to here that can handle these kinds of data set sizes. But when we compare it with a bunch of other sort of somewhat naive approaches based on techniques we've done in the past, and this one up here that came out recently, again, we're showing consistently better results in terms of ADE and FDE. And not only are we doing well in terms of performance, but also because of the way this is done. Again, you can do it incrementally and sort of run SILA, and you get pretty good times, but SimFuse is quite a bit faster. And like I said, it keeps the model size actually quite a bit smaller than SILA does, in fact, because there's a smarter way of combining things together. And again, the size will grow. We can't sort of stop it from growing without a pretty significant impact on performance. But on the other hand, we can slow the growth down, and that's the key at this point. So the third part of this work then has been thinking about, again, going back to the planning notion, and you're often thinking about these models that are based on deep learning. And so as we were in this case here, you're thinking about that prediction capability. How confident can we be in what the prediction is of what both the planner is going to do, but also what the humans are going to do as well. So the point being that there's a lot of techniques out there leading to sort of, promising algorithms in the prediction of these pedestrians based on sort of LSTM and graphical networks and adversarial networks. But, as has been made clear recently, just how small a perturbation, and these are primarily in the case of images, small perturbations to the images, and you end up with very confident neural nets that are making very dumb mistakes. And the point being, we need to come up with ways of making sure that we understand whether or not, oops, that's the church next door. So we have sort of this issue of lack of robustness in the neural nets based on the planning and perception in the presence of, we describe it as adversarial, but that's just thinking about worst case. And we aren't necessarily expecting an adversary, but we want to make sure we understand what the worst can be that can happen. And so this was a case actually with Tesla with very small perturbations to the outside world led to a very different result than you would expect the vehicle to be executing itself. So what we've been looking at here, and others have done this as well, is trying to understand what the output is of a neural net. So again, you're basically saying if there are possible perturbations on the input, which again is sort of shown here by this 2x2 representation, so sort of a two-space input set with uncertainty. And the point being that we're trying to take that uncertain set, run it through this giant neural net, which each element in here is a nonlinearity. And so you're trying to understand effectively what the set of outputs will be given the set of inputs. So again, this is an uncertainty set over here. We're trying to run that through this neural net and then predict what the output will be. So the black dots are if you just do a bunch of Monte Carlo stuff, you sort of get these, sort of output here. We're trying to come up with a way of sort of outer approximating that, which is what our black line is doing. And the key idea here was that if you just try to think about the entire uncertainty set as one big blob, you do a really bad job of making the prediction of that uncertainty all the way through. But by segmenting it and resegmenting it and redoing the calculations, we actually found that we can much more accurately predict, which is sort of shown here in the animation. And so we can actually get to a much tighter bound. The point being that what we were looking at here was a much simpler prediction method for each of the calculations we're doing, but we were focusing on the segmentation. So the calculations themselves got a lot faster than other people have been looking at, but then we had to repeat those calculations many times because of the segmentation. So, but the point was that it was a good trade-off, is the bottom line. And that showed up in the recent paper as well in the letters of the Control Systems Society just came out. So at a high level is sort of roughly what we're trying to do. When what that looks like then is sort of you've got a learn policy and trying to robustify what the planning can do. So again, it's pretty crude, but what you're looking at here is the blue robot sort of hallucinating and sort of anticipating what I guess the orange robot is anticipating what the blue robot might do. It turns out it's just driving a straight line, but the orange robot is concerned about what it might do. And if you have a poor prediction sort of capability and analysis tool, you're not with a very conservative result of what the orange robot ends up doing as a result. You can tighten that using the techniques that we just developed and end up with a much faster sort of, well, for the orange agent getting to the goal much faster because it's making much less conservative assessment of what the blue agent can do using the same input. So this is safe, but conservative. This is safe and faster. And so that's ideally what we're looking for here. So again, in terms of the sort of challenges, you're looking at scalability of all these techniques to these sort of the crowded scenarios. So you're trying to understand how to, in the work we've done so far, we had not been modeling the interaction between pedestrians and sort of themselves. That gets to sort of the next level of the prediction capability. We're just been sort of anticipating how the humans might be interacting with the environment and given the context of the environment. But if you then start thinking about how they interact with each other, that gets to another layer. And we've sort of thought about this, I mean, in the sense of possibly thinking about multi-agent RL as opposed to just sort of single agent RL. But if you worked in the multi-agent domain, you know that that's the scalability problem you have to address there. Again, continued generalizability and transferability to new data sets, but I think also just trying to make sure we can get new data sets. And so some of the challenge problems described earlier might be heading in that direction as well. Sorry about the cough. And so again, just helping us understand and anticipate some more of the anomalous behavior that humans might be exhibiting will sort of ultimately come from these data sets and mechanisms for fusing the models over time. So with that, I'll stop. Hopefully I'm taking up too much time. But again, some of the work we're looking at is transferability, incremental learning, distributed learning, and certifiable learning. And I think these are beginning to address some of the key challenges in this area. And thank you for your time.
Thank you. This was very informative, a lot of materials. I'm sure there must be some questions in the audience.
Yeah, I'll just skip ahead so you can see that. I'll just put these on the screen so that you can at least pause if you want to see them later.
I actually have a question. Thank you so much for this talk. I especially enjoyed some of the perspectives you shared towards the end of the talk about how we can robustify our planners and our predictors. What I want to ask was, typically when developing these human motion predictors, it's really difficult to capture rare events or behaviors, because the majority of the data that we use and use for training and for evaluation sort of demonstrate maybe average case behaviors of pedestrians or other drivers. So I'm curious about your perspectives on how we can really design predictors which are really capable of capturing both those average case behaviors that we really do want to be actually using on the day-to-day, but also these tail end behaviors that really matter.
Yeah, well, there's a bunch of challenges here. One is that, if we only collect data that has the average cases in it, then you end up with what I often describe as sort of the Swiss cheese problem, where you have a neural net that's based on sort of average stuff, and it sort of missed all these corner cases. And the question is, so how are the corner cases actually really captured in this? So one of the things that I didn't really mention, but part of this sort of data set collection is actually trying to build in a design of experiments exercise. So, if you, and I think this has been one of the challenges in the autonomous vehicle industry, is that, people claim, oh, we've driven tens of millions of miles. Yes, but have you seen enough of the corner cases that you're confident you can roll out the technology? And the answer is no. So what you really need to do is be driving probably fewer miles, but driving the right sets of miles. And I think the same situation here. It's just that what I often find with these, when people do design experiments, they go out and sort of end up scripting something, and everything ends up looking like just a cartoon of the real world. And so the question is, can you create, situations that you think might can you analyze situations that you think might be perplexing, that you want to collect data for to understand better and capture better, and then replicate that in the real world without it looking like a bunch of actors stick walking around. So that's one set of points. The other is, I think that really the corner cases in this type of work get captured by saying, look, can we learn based on average models, average data, and then through these uncertainty blocks, basically the sort of go in and perturb it and say, well, what if this happened instead? What if that happened instead? But what's then really missing is an understanding of how does one insert that type of uncertainty into this type of work? Because what tends to happen in this field, I'm sort of working in this field, so I can criticize it, because I'm criticizing myself essentially, is you often end up analyzing what you can, not what you should, right? Because the analyzing what you should is sort of hard, right? So you don't do that because it just doesn't scale or whatever. So you end up with a lot of people doing LP bowls and stuff like that because we can. But the question is, what should you be analyzing? Where should the uncertainty actually be entering into the problem, and how should it really be described? And that's really the next set of these directions. This is the work that's doing what we can. Now we have to sit down and start figuring out what we should be doing. And so that really is a case of sitting down and again, thinking about what are these corner cases and how do we best capture them in this type of certification work? Can we? And if we can't, then we have to go out and collect more data that actually helps us to get more confident about the models. So that's a great question.
Yeah, thank you so much.
Thank you. I recall there were other questions from the audience, some raised hands. Nope. All right, then I actually have a question as well. So for the SILA approach, it looks like a very interesting one to learn these motion primitives in the environment, which would be explicitly semantics aware and obstacle aware. I'm curious, how fast can you change notice the changes in the environment? And on the other hand, how robust you are to outliers with this approach when the current motion of an agent cannot be explained by this learned model? Can you elaborate on this a little bit?
Yeah, it's a great question. I mean, it's the classic difficulty with any estimation problem is noise, right? I mean, is that noise or is that just like something new? And so that's, as I don't want to just say, well, that's where the challenge is, but I mean, that's effectively where the challenge is. I mean, so you will often end up in situations like this where there will be sort of this magenta blob down here, which is just sort of quote everything else, right? It's sort of things that don't look like everything else. And then you can either just have a whole bunch of models, which are then they're independent, sort of their own independent thing, or you just clump them together as, I don't really know what those are, and wasn't able to model them accurately. And that's often the way these semantic labelings go, that you clump together the things you can, and then there's a big bin of other stuff. And so it's not, it's not a great solution, but on the other hand, it is a way of sort of avoiding getting models that just end up being enormous. And you really want to identify things which make sense. I mean, the question I think was asked last time, how do these make sense? And the point is, a lot of these macro actions do end up looking like this, and they do make sense, and the transition models make sense. But that's in part because we're sort of putting a lot of the noisy stuff we don't understand into just a big bin of other stuff. And again, if you have agents you can track, and then you don't end up with a lot of noise. But when you're using these models, you will have a situation where an agent, like we do a lot of work at crosswalks, and you'll see agents sort of come across and then maybe turn around and go back or something like that for reasons we had never seen before. And the question is that you want to really capture that as a new model. I mean, it's a behavior. The question is, if it's only one agent ever showed that behavior, is that something you want to capture in a model, or do you just want to classify it as sort of not the same as everything else? So the point being that the model ends up capturing the dominant behavior, and this bin of everything else is just the stuff we don't recognize. And so when you're using this model, you would sort of then begin to see a behavior where maybe the agent's going across, you're making a prediction, and if they turn around and go back, and you're able to capture that behavior with your sensors, then you would recognize it as not being part of this anymore. It's now just sort of gone into this other clump, and we may not be able to recognize it, but we know it's not one of the other things that we've seen.
Thank you. This was very interesting. I guess for the sake of time, we must move on with the next speaker, but okay. Thank you for the presentation.
All right.